So let's look at some more functions that are defined initially as parametric equations, and then see like I want to look at this number 6. I know I'm jumping around a bit, but I want to look at this example, and it says describe the curve represented by the parametric equations: x defined as cosine and y defined as sine. And so sometimes an easy way to do that is to eliminate the parameter to see if it's something that you already recognize. But this one's a little bit tougher to use substitution to eliminate the parameter, because if you remember the last examples, you could solve for t in terms of x and substitute it back in and get the y. I'm not sure if I want to do that, because that would mean I have to introduce an inverse cosine function, and that that involves a restriction potentially of the domain. And so what I'm going to do, and it might seem like a little unconventional initially, but what I'm going to do is actually I'm going to square both sides. And the reason I'm going to square both sides is because I'm going to try to create an identity of something I already know. So if I square both sides here, okay, go away. So that's x squared, there we go, thank you, equals, and when you square this, so you're squaring the 2, so that's 4, you're squaring the cosine function, cosine squared, but you don't square the angle, it's still pi over 6t. And then I square this, y squared equals 5 squared is 25, sine squared of pi over 6t. Okay, so now I have a cosine squared, I have a sine squared, and what I'm shooting for is I know the Pythagorean identity. Sine squared plus cosine squared equals 1. So I need to divide this by 4 and divide this by 25, respectively. So now that first equation could become x squared over 4 equals cosine squared of pi over 6t. And then this equation can become y squared over 25 is equal to sine squared of pi over 6t. Now my pen is obviously not cooperating as much as I want it to be. Okay, now I have cosine squared, I have sine squared. Let's add the two functions together. I'm going to add those up. And the left side just becomes x squared over 4 plus y squared over 25. Now, the right side is cosine squared of some angle plus sine squared of some angle. And it doesn't really matter what you call that angle. It doesn't matter that there's a variable in it, because the Pythagorean identity says, wow, that this is awful. No, plus sine squared of pi over 6t, that as long as your angles are the same, that sine squared plus cosine squared equals 1. So this whole thing can be thought of as just a 1. So we'll erase that and substitute it in as a 1. And we've eliminated the parameter. And so then we get 1. Now, at one point, this is something that we studied last semester. It's a conic section, sort of like a circle. Both quadratics are positive, but because one is stretched more, like the y is stretched more, then this is an ellipse. And remember, definition of ellipse is x squared over a squared plus y squared over b squared equals 1. And as long as it's just an x, it's not like x minus 2 quantity squared or y minus 3 quantity squared. In the center of the origin, you go out square root of a squared, so you go out a in the x direction and go out b in the y direction. So if I were to sketch this path, without the parameter, no time, so I don't know how fast or what direction, and that's going to be what the next video is going to cover, but I'd go out 5 in the y direction, and I go out 2 in the x, and I make my ellipse. So the thing that I get really excited about is that an ellipse is not a function, because it does not pass the vertical line test. But if you create the ellipse as a set of parametric equations, then it does become a function. And so that's one of the advantages of looking at parametrics, is that you can now represent non-functions, through the lens of time, they can now be represented as functions. Now, another thing I want you to think about too is the fact that from the get-go, as soon as we start being familiar and recognizing these parametric functions that are ellipses or circles, you can get the dimensions right from the equation. I mean, think about x here, and there's a coefficient of 2. And think about, oh, well, there's 2 in the x direction. And then the y is 5, and there's 5 in that direction. So that's another way to tell the size of this ellipse if you have sine squares and cosine squares. So a good exercise could be to pause the video and try to try to come up with like this particular equation. But the other thing I want to think about too, it does say describe the path or describe the curve. So I have a nice image of it, but we should probably just put t equals 0 just to see, where does this thing start? Because it does go from 0 to 18. So if I say, okay, let's let t be 0. So when t is 0, this is a 0. So we're evaluating the cosine of 0 and the sine of 0. The cosine of 0 is 1. 1 times 2 is 2. And then the sine of 0 is 0. So this actually starts at 2, 0, at t equals 0. And then, so then if I want to come up with another nice value, like letting t equal 1, or t equal 2, or t equal 3, because those are all like divisible by, like, in terms of like making nice angles, I'm actually going to pick t equals 3. And the reason I picked t equals 3 is because 3 pi over 6, which is pi over 2. And so like that was an easy way for me to do that. Cosine of pi over 2, which is cosine of 90, is 0. And then here, the sine is 1 at pi over 2, and 1 times 5 is 5. So I know at t equals 3, I'm up here. So it started here, and I'm going up in this direction. And so the other thing I'm thinking about too is that it's taking 3 seconds to get up here. And if it's going at a consistent speed, it'll be 3 more seconds. So it's a total of 6 seconds. And then 3 more seconds, there's 9. And 3 more seconds, there's 12. So at time equals 12, I'm claiming I should be at the exact same spot. And if you put 12 into this, look at that, 12 pi over 6, that's 2 pi. So you're the exact same cosine sine. And in fact, if you think way, way back, 2 pi over b was what we studied to figure out what the new period of the function was. And if you take pi over 6 and put that in, 2 pi over 6, you will get 12 is the new period. And that represents how long it's going to take to go around this ellipse. So that's another thing I want to analyze. Like there's some things that we studied last semester or earlier this chapter earlier this semester, I should say, in a previous chapter, that they're going to be super helpful. Okay, so it's a lot of analysis on that. Okay, so number 7, same idea. I'm going to initially divide the -3's over. Not that it mattered, but so we have x, oops, and I'm already squaring, but I won't get too far ahead of myself. So x divided by -3 equals cosine of pi over 2 t, and then y over -3 equals sine of pi over 2 t. Okay, so let's square both sides. So that becomes x squared over 9 equals cosine squared of pi over 2t. And then this one becomes y squared over 9. So again, utilizing Pythagorean theorem, or the Pythagorean identity. Oops, there we go. There's a little delay there in the center of my screen for some reason. Pi over 2t. Okay, so now, again, as long as the angles are the same, it doesn't matter what they are, or if there's a parameter there, I'm going to go ahead and add them up. Oops, I thought I picked a different color. All right, April Fool's on me. Let's see, let's pick this color. Okay, so then that's x squared over 9 plus y squared over 9 is equal to 1. And again, this is an ellipse, but this ellipse actually is being stretched in the same amount in both the x and the y, so it's a special ellipse with no eccentricity whatsoever, otherwise known as a circle. And then x squared over 9, so I could go out 3 in the x and 3 in the y. So in this particular ellipse, like I said, it's circular. So I'll go ahead and go out 3 in all the directions. Let's see, maybe pick this orange. 1, 2, 3. 1, 2, 3. 1, 2, 3. Wow. 1, 2, 3. I can count to 3. Now this is gonna look not so super circular. I'm not really all that great at using my tablet here to draw that circle. But then I also want to know, where does this start? I have some negatives here, so that makes me a little bit cautious of where this might be going and in a direction it might be going. And again, kind of leading us up to the next video, because that's something we're going to want to analyze. So let's let t be 0. Make a nice little table of, t equals 0. So then, so like when time equals 0, we're doing the cosine of 0, which is 1, but it's 1 times negative 3. So, t, x, y. So 0, we're at negative 3, and then the y value is still going to be 0. So I'm going to be starting here. So there's t equals 0 right there. Okay. And then let's see. Well, I know that 2 pi over this, 2 pi over 2 is going to give me the new period. So the new period is actually going to be 4 seconds. So it's going to take me a second to get to the quadrantal values. So let's let t equal 1. And then again, kind of hindsight, that gives you pi over 2. So when t equals 1, the cosine of pi over 2 is 0. The sine of pi over 2 is 1, but 1 times negative 3 is negative 3. So we're down here at negative 3 for t equals 1. So we're still moving, it looks like, in this counterclockwise direction. It's not always going to be the case. So then I could let t equal be 2, and that's going to give me a value of cosine of pi, which is negative 1 times negative 3, which gives you a positive 3 and a y value of 0. So you're there at t equals 2. And then, subsequently you plug in the 3, you're up here, 4, you're up here. And I mentioned, like, we might be going different directions in the next video, and that's all going to depend on where are these negatives at that are in front of the coefficients. And then the other thing I wanted to make mention that I forgot in the last example is that if you have it through 16, that just means you're just going to be going around so many times. So if it takes 4 seconds to go around once, and you're going through 16, then you're just repeating that 4 times. Okay, so one more on this. I know it's a little bit longer actually than I anticipated, but if you listen to and follow along, I think there's some really good discussion or some good analysis here. So then the last one, if I throw a curveball at you, so to speak, there's no more sines and cosines, it's tangents and secants. But if your mind's already in that thought process of Pythagorean identities, then you remember, or you might remember that there's one that involves tangent and secant. But the tangent and secant one, so remember there's sine squared, wow, this is just terrible today. Sine squared theta plus cosine squared theta equals 1. So if I want to create the one that has tangent and secant, I'm going to divide everything by the cosine function. And let's see how this turns out. Cosine squared theta, divide this one by cosine squared theta, divide this one. Again, just trying to remind you where these come from. There's definitely a delay in my computer. So that's tangent squared plus 1 equals secant squared. Tangent squared theta plus 1 is equal to secant squared of theta. Okay. So then if I have tangents and secants and I want to get rid of the parameter, in other words, isolate the 1, I'm going to want to subtract the tangent to the side. So 1 is equal to secant squared of theta minus tangent squared of theta. So it's actually that variation of our identity, the subtraction is what's going to get rid of that parameter. So when I square these, I'm not going to add them. I'm actually going to subtract. I want to make sure I do secant squared minus the tangent squared. So when I square this, I'm going to get y squared equals secant squared. For some reason on this side of the screen, it seems to be better. So y squared, as soon as I said that, look what happened. Not better. 3t. And then when I square this one, it's x squared equals tangent squared of 3t. And as long as those angles are the same, when you subtract, you get y squared minus x squared is equal to secant squared minus tangent squared, which is 1. And so now I know this is a hyperbola, not an ellipse or a circle, because one of our variables is negative, one of our quadratics. And so then again, at one point, in our a values are still the same. So like we could have thought of that as 1 over 1 had there been any coefficients to divide over. And then you still go out the square root in each of those directions. And I won't be as particular in this in this chapter about graphing these, but you should have an indication or an idea or recall a few things that look familiar. Like if I go at the square root of 1, which is 1 in the y direction, and I go at the square root of 1 in the x direction, I make my little box, and remember that's going to determine the slope of our asymptotes. Okay, let's see how that lags up there. That's kind of fun. And then I can go ahead and draw the two oblique asymptotes. And then that divides it into 4 quadrants, or 4 regions, I should say. And so the question is it opening left and right or up and down? And because this one's first, aka positive, then it's opening in that particular direction. So then I would pick my favorite color today, right now, purple, and then go ahead and draw a tangent to that box, and it's opening in the y direction. And we go ahead and hug the asymptotes because those predict the behavior of our graph. Okay, excellent. So again, here's our hyperbola, and normally a hyperbola is not a function, but through the lens of parametric equations, we can represent it as a function. And then again, that's kind of nice as we start to move into calculus. That's exactly what we want to do. Is we want to study functions, and we want to study functions change over time, which again, it makes parametrics a perfect lens to analyze those. Okay, so longer video than I thought, but hopefully that this made sense, and you could try a couple examples on your own.